Chronos Unbound, a journey into the mystery of time. What time is it? It's a simple question, one we ask every day. We look at a clock, a watch, a phone, and we get a simple answer. Time for us is a tool. It's the rigid, predictable metronome that governs our lives, scheduling our meetings, our meals, our sleep. It's the mundane ticking that marks the seconds, minutes, and hours. But behind that simple, practical facade lies perhaps the deepest, most persistent mystery in all of science. What is time? Is it a great river, as the poet Ovid imagined, carrying us all relentlessly forward in its current? Is it a fourth dimension, as real and traversable as length, width, and height? Or is it, as some of the most advanced physics now suggests, a grand illusion, an emergent property of a reality far stranger than we can imagine? For millennia, we have tried to grasp it. Our ancestors looked to the heavens, charting the regular motions of the sun, moon, and stars to mark the passage of days, months, and years. We built sundials and water clocks, sandglasses, and intricate mechanical devices, all in a relentless quest to tame and measure this invisible, intangible force. Today, our atomic clocks are so precise they would lose only a few hundred seconds over the entire 14 billion-year history of the universe. We have become masters of measuring time, yet its fundamental nature remains as elusive as ever. This is the story of that quest, a journey from a clockwork universe governed by a single universal beat to a cosmos where time can stretch and shrink, where past and future are locked in a thermodynamic dance, and where, at the very bottom of reality, time itself may not exist at all. This is the story of time, the most mysterious dimension, the clockwork god and the cosmic river. Our modern scientific journey into time begins with one of the greatest minds in history, Sir Isaac Newton. In the late 17th century, as he formulated his laws of motion and universal gravitation, Newton gave us the first clear mathematical picture of time. And in his monumental work, the Principia Mathematica, he laid down a concept that feels deeply intuitive, one that resonates with our everyday experience. He called it absolute, true, and mathematical time. In Newton's own words, this absolute time, of itself and from its own nature, flows equably without relation to anything external. Think of it as a universal clock, a cosmic metronome ticking away at a perfectly steady rate, everywhere in the universe, for all of history, completely independent of anything that happens within it. Whether a planet orbits a star, a pendulum swings, or the universe is entirely empty, this absolute time flows on, unchanged and unchangeable. But why did Newton need this abstract, unseeable concept? Because he was a brilliant and practical physicist who knew that every real clock he could observe was flawed. He knew that the natural days, measured by the rotation of the Earth, were actually unequal, and that astronomers had to constantly apply corrections to make their measurements work. He knew that pendulum clocks were affected by local conditions, like gravity, which was later confirmed to vary with latitude. No physical process, he concluded, could serve as a truly infallible timekeeper. So he proposed that these flawed, measurable times were merely relative, apparent, and common time, sensible measures of duration that we infer from motion. Our clocks, our calendars, the rising and setting of the sun, these were all just imperfect shadows of a true, underlying reality. God's perfect time, the absolute duration flowing in the background. This distinction between an unobservable, perfect reality and our flawed, perceived reality is a powerful idea. It framed time as a fundamental, independent entity, a kind of container or stage upon which the events of the universe played out. But even as Newton's physics conquered the scientific world, this idea of absolute time didn't go unchallenged. His contemporary, the philosopher and mathematician Gottfried Leibniz, mounted a powerful counter-argument. For Leibniz, the idea of time existing without change was nonsensical. He argued that time is not a container, but a relationship. It makes no sense, he said, to speak of a period of time without any events happening. Time is simply the ordering of those events, one after another. Space, likewise, was just the relative location of objects. This debate between Newton and Leibniz, between the container view and the relational view, set the stage for one of the greatest revolutions in the history of thought. It was a deep philosophical conflict about the very existence, the ontology of time. Is time a real thing that flows on its own? Or is it just a concept we derive from the relationships between things that change? For over 2 centuries, this remained a philosophical puzzle. Newton's physics worked so perfectly that his idea of absolute time reigned supreme. But a crisis was brewing in physics, a conflict between Newton's laws of motion and the new laws of electromagnetism. To solve it, a young patent clerk in Switzerland would be forced to re-examine the very foundations of space and time. In doing so, he would show that the relative time Newton dismissed as a mere measurement was, in fact, the only time that truly exists. The idealized, perfect clock was about to be shattered. Einstein's revolution, the malleable fourth dimension. For 200 years, Newton's vision of a clockwork universe, ticking to the beat of a single absolute time, was the bedrock of physics. But at the turn of the 20th century, that foundation began to crumble. The problem was light. According to the laws of electromagnetism, the speed of light in a vacuum is a constant, a universal speed limit. But according to Newton's mechanics, speeds should be relative. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone on the ground sees the ball moving at 120 kilometers per hour. It's simple addition. But what if you turned on a flashlight? Would the light from that flashlight travel faster than light from a flashlight on the ground? The laws of electromagnetism said no. The speed of light is always the same, regardless of the motion of the source or the observer. This contradiction was the crisis that led Albert Einstein to his theory of special relativity in 1905. He started with 2 simple, radical postulates. First, the laws of physics are the same for all observers in uniform motion. Second, the speed of light in a vacuum is the same for all observers. For both of these to be true, something had to give. That something was Newton's absolute time. Einstein realized that if the speed of light is constant for everyone, then our measurements of distance and time must change depending on our motion. This led to a truly mind-bending conclusion, the relativity of simultaneity. Imagine a long, fast-moving train. A lightning bolt strikes the very front and the very back of the train at the same time, according to an observer standing on the platform beside the tracks. But for an observer sitting in the exact middle of the train, the light from the front strike reaches her before the light from the back strike, because she is moving towards the point where the front strike occurred. From her perspective, the 2 events are not simultaneous. The front of the train was struck before the back. This simple thought experiment delivered a fatal blow to the idea of a universal now. If 2 observers can't even agree on whether 2 events happen at the same time, then the notion of a single, absolute present moment for the entire universe is meaningless. It was Einstein's former professor, Hermann Minkowski, who gave this new reality its proper language. In 1908, he declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the 2 will preserve an independent reality." He showed that space and time were not separate entities, but were interwoven into a single, 4-dimensional fabric, space-time. Time was no longer a river flowing independently. It was a dimension inextricably linked to the 3 dimensions of space. This unification of space and time has a bizarre and beautiful consequence: time dilation. Time itself can stretch and shrink. There are 2 ways this happens. The first is a consequence of special relativity and is related to velocity. To understand it, let's use a famous thought experiment: the light clock. Imagine a clock made of 2 mirrors, with a single particle of light, a photon, bouncing between them. Each time the photon hits the bottom mirror, the clock ticks. For an observer standing next to the clock, the photon travels a straight path up and down. Now, imagine that clock is placed on a spaceship moving at a very high speed relative to you. From your perspective on the ground, as the clock moves past, the photon no longer travels a straight path up and down. Because the mirrors are moving, the photon has to travel a longer diagonal path to get from the bottom mirror to the top one, and another diagonal path to get back down. Here's the crucial part: the speed of light is constant for everyone. So, if the photon has to travel a longer distance from your point of view, but its speed hasn't changed, then the time it takes to complete that journey must be longer. From your perspective, the moving clock is ticking more slowly. This isn't an illusion or a mechanical defect. Time itself is passing more slowly for the moving object. The second form of time dilation comes from Einstein's general theory of relativity, published in 1915. This was his theory of gravity. It began with what he called his happiest thought. An observer in free fall doesn't feel their own weight. From this, he derived the equivalence principle. The effects of gravity are indistinguishable from the effects of acceleration. This led him to an even more profound conclusion. Gravity is not a force pulling objects together, as Newton had thought. Gravity is the curvature of spacetime itself. Imagine a stretched rubber sheet. If you place a heavy bowling ball in the center, it creates a deep curve in the sheet. If you then roll a marble nearby, it won't travel in a straight line. It will follow the curve created by the bowling ball, spiraling inwards. This is Einstein's gravity. Matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. And just as massive objects curve space, they also curve time. Clocks that are deeper inside a gravitational well, closer to a massive object like the Earth or a black hole, are in more intensely curved spacetime. As a result, they tick more slowly than clocks in weaker gravity, farther away. There are two types of time dilation: velocity-based dilation, which is explained by special relativity, and gravity-based dilation, which is explained by general relativity. Velocity-based dilation is caused by high relative velocity between observers. In contrast, gravity-based dilation results from a strong gravitational field, or more precisely, from curved spacetime. In velocity-based dilation, moving clocks appear to run slower compared to those at rest. In gravity-based dilation, clocks located in stronger gravitational fields run slower than those in weaker fields. Velocity-based dilation becomes most significant near the speed of light. Gravity-based dilation is strongest near very massive objects, such as black holes. A real-world example of velocity-based dilation is the extended decay time of muons in particle accelerators. A real-world example of gravity-based dilation is the need for clock corrections in GPS satellites, which are farther from Earth's gravitational field. These ideas might sound like abstract science fiction, but the proof is all around us, woven into the fabric of our modern world. The most stunning example is the Global Positioning System, or GPS, that many of us use every day. The GPS network consists of dozens of satellites orbiting the Earth at high altitudes and high speeds. To pinpoint your location, your receiver needs to calculate the time it takes for signals to arrive from at least 4 of these satellites. This requires nanosecond accuracy, but the clocks on those satellites are subject to both forms of time dilation. First, because the satellites are moving at about 14,000 kilometers per hour relative to us on the ground, special relativity predicts their clocks should run slower than ours by about 7 microseconds or 7,000 nanoseconds every day. But that's not the whole story. The satellites are also about 20,000 kilometers above the surface, where Earth's gravity is significantly weaker. According to general relativity, this means their clocks should run faster than ours by about 45 microseconds per day. The net effect is that the clocks on GPS satellites gain about 38 microseconds, 38,000 nanoseconds, on ground-based clocks every single day. It may sound tiny, but if engineers didn't account for it, the system would accumulate errors of about 10 kilometers per day, making it completely useless within hours. To counteract this, the atomic clocks on the satellites are deliberately built to run slightly slower on Earth, so that once they are in orbit, they tick at the correct rate relative to us. The GPS system is a continuous, planet-wide experiment that proves relativity isn't just a theory. It's a non-negotiable engineering principle of our civilization. The evidence doesn't stop there. In particle accelerators, we create unstable particles called muons. At rest, a muon decays in about 2.2 microseconds. But when we accelerate them to 99.5% the speed of light, we observe them lasting about 10 times longer. From our perspective in the lab, their internal clock has slowed down so dramatically that they have time to travel much farther before decaying. 000 kilometers above the surface, where Earth's gravity is significantly weaker. According to general relativity, this means their clocks should run faster than ours by about 45 microseconds per day. The net effect is that the clocks on GPS satellites gain about 38 microseconds, 38,000 nanoseconds, on ground-based clocks every single day. It may sound tiny, but if engineers didn't account for it, the system would accumulate errors of about 10 kilometers per day, making it completely useless within hours. To counteract this, the atomic clocks on the satellites are deliberately built to run slightly slower on Earth, so that once they are in orbit, they tick at the correct rate relative to us. The GPS system is a continuous, planet-wide experiment that proves relativity isn't just a theory. It's a non-negotiable engineering principle of our civilization. The evidence doesn't stop there. In particle accelerators, we create unstable particles called muons. At rest, a muon decays in about 2.2 microseconds. But when we accelerate them to 99.5% the speed of light, we observe them lasting about 10 times longer. From our perspective in the lab, their internal clock has slowed down so dramatically that they have time to travel much farther before decaying. This is a routine confirmation of time dilation. The precision of modern atomic clocks has allowed for even more astonishing tests. In 1971, the Halfel-Keating experiment flew atomic clocks around the world on commercial airliners and measured the tiny time differences predicted by relativity. More recently, physicists at the National Institute of Standards and Technology (NIST) have measured gravitational time dilation between two clocks separated by a height difference of just 33 centimeters, about 1 foot. They found that the higher clock, being in slightly weaker gravity, ran infinitesimally faster, exactly as Einstein predicted. In 2022, this was pushed to an even more incredible extreme. A measurable time difference between clocks separated by a single millimeter, the width of a pencil tip. This confirms a bizarre but undeniable fact of our reality. Your head is aging ever so slightly faster than your feet. Einstein's revolution was complete. The absolute universal clock of Newton was gone, replaced by a dynamic, malleable, and personal time, a dimension woven into the very fabric of the cosmos. The arrow of time, why yesterday is not tomorrow. Einstein gave us a new picture of time, a dimension intertwined with space, capable of stretching and shrinking. But his theories, as revolutionary as they were, left a fundamental mystery untouched. Why does time seem to move in only one direction? We are born, we grow old, we die. We remember the past, but we cannot remember the future. A glass falls and shatters into 1,000 pieces, but we never see 1,000 pieces of glass leap off the floor and reassemble into a glass. This is the great asymmetry of time, the one-way street from past to future that physicists call the arrow of time. The puzzle is this: the fundamental laws of physics that govern the interactions of particles don't seem to care about the direction of time. The equations of mechanics, of electromagnetism, even of relativity and quantum mechanics, are largely time reversal invariant. If you were to watch a video of two billiard balls colliding, it would look perfectly normal whether you played it forwards or backwards. At the microscopic level, there is no preferred direction of time. So where does this powerful, all-pervading arrow that governs our macroscopic world come from? The most widely accepted explanation comes not from the laws of motion, but from the laws of heat and disorder, thermodynamics. Specifically, the second law of thermodynamics. The second law introduces a quantity called entropy, which can be thought of, roughly, as a measure of disorder or randomness. Imagine a neat stack of papers on your desk. This is a highly ordered, low-entropy state. Now, imagine you throw those papers into the air and let them fall. They will land in a scattered, disordered mess, a high-entropy state. It's the same for a cup of coffee and a dash of cream. When they are separate, the system is ordered and has low entropy. Once you mix them, the molecules become randomly distributed, and the system is in a state of high entropy. The second law of thermodynamics states that in any isolated system, like the universe as a whole, total entropy can never decrease. It will always increase or, at best, stay the same. Things naturally progress from order to disorder. This relentless, one-way increase in entropy provides a powerful physical basis for the arrow of time. The reason we see eggs break but not unbreak is because the shattered egg is a far more disordered, higher entropy state than the whole egg. There are vastly more ways for the atoms to be arranged in a mess on the floor than in the perfect structure of an eggshell. The universe simply moves towards the most probable state, and the most probable state is always one of greater disorder. But this explanation immediately raises an even deeper question. If the universe is constantly moving towards a state of higher entropy, that must mean that it started in a state of incredibly low entropy. This idea is known as the past hypothesis. For the arrow of time to exist, the universe must have been born, at the moment of the Big Bang, in a highly specific, exquisitely ordered, and statistically miraculous state. The entire 13.8 billion year history of the cosmos, the formation of galaxies, stars, planets, and life, is simply the universe unwinding from this special initial condition, moving inexorably towards a future state of maximum entropy, a uniform, featureless equilibrium known as the heat death of the universe. This thermodynamic arrow seems to be the master arrow from which all others are derived. Physicists also speak of a cosmological arrow of time, which points in the direction of the universe's expansion. The universe is getting bigger, not smaller. And then there is the psychological arrow of time, the one we experience most intimately. We have memories of the past, but not of the future. Are these three arrows, thermodynamic, cosmological, and psychological, all pointing in the same direction by coincidence? Or are they deeply connected? The link between our minds and the cosmos appears to be profound. The very act of forming a memory is a physical process. It involves creating ordered structures in our brain, specific patterns of neural connections that are correlated with a past event. Creating this order within the small system of your brain requires energy, and this process is irreversible. It dissipates heat and increases the total entropy of the universe as a whole. In other words, you can only form a memory of the past because the second law of thermodynamics is true. Our subjective experience of time's one-way flow is not just an illusion. It seems to be a direct consequence of the fundamental physical laws governing the very matter that makes up our brains. This creates a stunning chain of explanation, a detective story that traces a clue from our most personal experience all the way back to the origin of everything. The story starts with a simple question. Why do I remember what I had for breakfast this morning, but not what I will have for dinner tomorrow? The answer is that memory is a physical process of creating order in the brain. Why can this process only happen in one direction? Because it must obey the second law of thermodynamics, which dictates that overall disorder, or entropy, must always increase. Why does entropy always increase? Because it started out in a state of near-perfect order. And why was the universe born in this incredibly improbable low-entropy state? That is one of the greatest unsolved mysteries in all of cosmology. The arrow in our minds points in a specific direction because it is tethered to an arrow that was fired at the very beginning of time itself. Quantum time, the universe at its strangest. Just as we thought we were getting a handle on time, with Einstein's flexible spacetime and the thermodynamic arrow, we arrive at the edge of a new abyss, the quantum realm. And here, our understanding of time is thrown into its greatest crisis yet. The conflict is so profound that physicists call it, simply, the problem of time. The problem arises from a fundamental clash between our two pillars of modern physics. In Einstein's general relativity, as we've seen, time is dynamic and relative. It is part of the fabric of spacetime, warped by gravity, and its passage depends on your motion and location. It is not a fixed background. It is an active player in the cosmic drama. But in quantum mechanics, the theory of the very small, time plays a completely different role. It is treated as an absolute universal background parameter, a rigid, ticking clock that is external to the system being described. In the standard Schrödinger equation, which governs how quantum states evolve, the T for time is just a number, a parameter that marches forward, completely unaffected by the quantum weirdness it oversees. This treatment of time in quantum theory is much closer to Newton's old idea of absolute time than to Einstein's. This conceptual chasm becomes a full-blown crisis when we try to create a theory of quantum gravity, a theory that unites relativity and quantum mechanics to describe situations where both are important, like inside a black hole or at the Big Bang. When physicists try to write down an equation for the quantum state of the entire universe, they get a bizarre and disturbing result. The equation, known as the Wheeler-DeWitt equation, is supposed to describe how the wave function of the universe, denoted by the Greek letter psi, evolves in time. But the equation that emerges is, schematically, h psi equals 0. The Hamiltonian h, which normally governs time evolution, acts on the universal wave function to give 0. There is no time variable, no t, anywhere in the equation. This is the frozen formalism problem. Taken at face value, it seems to imply that at the most fundamental level, the universe is static, unchanging, and timeless. Nothing ever happens. This is, of course, in stark contradiction to our every experience. But perhaps this isn't a failure of the theory, but a profound clue about the nature of reality. Maybe the universe isn't frozen in time. Maybe it is fundamentally timeless. The flow of time that we perceive might be an emergent property, a feature that arises only for an observer who is inside the system, looking at one part of the universe relative to another. Recent experiments have lent support to this idea. By entangling two photons, physicists have shown that a static, unchanging global state can be seen as evolving by an internal observer who uses one of the photons as a clock to measure the other. From the outside, nothing happens. From the inside, time emerges. The problem of time, then, is transformed from a paradox into a research program to explain how our familiar, flowing time arises from this deeper, timeless quantum reality. This strangeness extends to other quantum phenomena that challenge our classical notions of causality and time. Consider quantum tunneling. This is a well-verified effect where a particle, like an electron, can pass through an energy barrier that it classically shouldn't have enough energy to overcome. It's as if a ball could roll partway up a hill and suddenly appear on the other side without ever having reached the top. This raises a thorny question. How long does the particle spend inside the barrier? The very question is problematic because according to classical physics, it's never there. The debate over this tunneling time is fierce. Some experiments have suggested that the effective speed of the particle during tunneling is faster than light. This seems to violate causality. However, most physicists agree that this effect cannot be used to send a controllable signal faster than light. The outcome is probabilistic, and you can't decide when a particle will tunnel. The ambiguity highlights how, at the quantum level, our intuitive ideas of trajectory and duration simply break down. Then there is quantum entanglement, what Einstein famously called spooky action at a distance. When two particles are created in an entangled state, their properties are linked in a way that defies classical intuition. For example, their spins might be correlated. If you measure the spin of one particle and find it to be up, you will instantly know that the spin of the other particle is down, no matter how far apart they are, even if they're on opposite sides of the galaxy. This correlation appears to be instantaneous, faster than light. But once again, this spooky connection cannot be used to send information and violate causality. The outcome of your measurement is fundamentally random. You can't force the particle to be spin up in order to send a 1 to your friend across the galaxy. All you can do is measure it, get a random result, and then later, by communicating at normal light-speed limited methods, you and your friend can confirm that your random results were perfectly correlated. Entanglement doesn't break causality, but it does reveal a deep, non-local connection in the fabric of reality. Some physicists are even exploring the idea of entanglement in time, where an event happening now can be correlated with a later event in a way that defies a simple, linear cause and effect story. The quantum world forces us to abandon our most cherished intuitions. It suggests a reality where time might not be a fundamental flow, but an emergent perspective, where a particle can be in a place it can't reach, and where distant parts of the universe can be connected in ways that are instantaneous yet silent. This is the strange, timeless backdrop against which the ultimate theories of reality are now being built. Is time real? The frontiers of physics. We've journeyed from Newton's absolute river of time to Einstein's flexible fabric of spacetime, and peered into the thermodynamic arrow that points from an ordered past to a disordered future. We've seen how, at the quantum level, time itself seems to vanish from our most fundamental equations. This leads us to the most profound question of all. Is time real? Is it a fundamental component of the universe? Or is it an illusion, an emergent phenomenon that arises from something deeper? This concept of an emergent universe is one of the most radical ideas in modern physics. The idea is that spacetime is not the bedrock of reality. Instead, it emerges from a more fundamental layer, much like the wetness and fluidity of water, are emergent properties that arise from the collective behavior of countless individual, non-wet H2O molecules. At our scale, space-time seems smooth and continuous. But if we could zoom in to the tiniest possible scales, the Planck length, about 10 to the minus 35 meters, we might find that space-time itself dissolves into a granular, pixelated structure. If time is emergent, it has staggering implications for our understanding of reality. For instance, it could fundamentally change our ideas about time travel. If time is not a pre-existing track that we move along, you can't simply travel back on it. A trip to the past might be more like trying to reconstruct a past state of the universe from its constituent quantum bits. But this could be impossible for the same reason you can't unmix cream from coffee. The information about the precise microscopic arrangement of the past may be irretrievably lost due to the relentless increase of entropy. The past, once it has passed, might simply dissolve back into the underlying quantum soup from which it emerged. This question, is time fundamental or emergent, lies at the heart of the divide between the two leading approaches to a theory of quantum gravity. These two theories offer starkly different visions of the nature of time. The first is string theory. In this framework, the fundamental constituents of the universe are not point-like particles, but tiny, one-dimensional vibrating strings of energy. Different vibrational modes of a string correspond to different particles, like an electron or a photon. Crucially, one of these vibrational modes corresponds to the graviton, the quantum particle of gravity. For these strings to exist and vibrate, however, they need a stage to perform on. String theory, therefore, presupposes the existence of a background spacetime. In this view, time is a fundamental coordinate, a real dimension that exists as part of the background. The theory does complicate the picture by requiring that this background spacetime has more dimensions than the 4 we perceive, typically 10 or 11 in total. The extra spatial dimensions are thought to be compactified, curled up into a shape so minuscule that we cannot detect them. But time remains a fundamental axis, part of the very definition of the universe in which the strings live and move. The second approach, loop quantum gravity, LQG, offers a more radical perspective. LQG is a background-independent theory, meaning it does not assume a pre-existing spacetime stage. Instead, it attempts to build spacetime from the ground up by applying quantum rules to space itself. It predicts that space is not continuous but is made of discrete, indivisible chunks, atoms of space, each with a quantum of volume. These atoms of space are woven together into a dynamic, evolving network called a spin network. In this picture, there is no fundamental time variable. The equations describe the relationships and evolution of the spin network itself, without reference to any external clock. At the most basic level of reality, according to LQG, there is no time. So where does our experience of time come from? One of the leading thinkers in LQG, Carlo Rovelli, has proposed a compelling idea he calls thermal time. He argues that time emerges from the interplay of quantum gravity and thermodynamics, or more fundamentally, information theory. At the fundamental, timeless level of the quantum loops, there are only relationships and processes. But we, as large macroscopic observers, can never have complete information about the microscopic state of this network. Our view is inherently blurry and statistical. According to Rovelli, it is this statistical, incomplete view that gives rise to thermal phenomena like heat. And, he argues, it is the very same mechanism that gives rise to the flow of time we perceive. Time, in this view, is a consequence of our ignorance, an emergent feature of our interaction with the world. This places modern physics at a profound fork in the road. String theory and loop quantum gravity represent a deep philosophical schism. Is time a fundamental part of the stage, as in string theory? Or is it an emergent feature of the play itself, as in loop quantum gravity? The answer will not just complete our equations. It will fundamentally redefine our place in the cosmos and the nature of the reality we inhabit. Cheating time, the physics of time travel. The idea of time travel has long been a staple of science fiction, a fantasy of correcting past mistakes or glimpsing the distant future. But is it physically possible? The answer, according to our best theories of physics, is a surprising yes and no. Traveling to the future is not only possible, It's an unavoidable consequence of the laws of nature. Traveling to the past, however, remains a far more speculative and paradoxical endeavor. Let's start with the future. A one-way ticket to tomorrow is guaranteed by Einstein's theory of relativity. As we've seen, time dilation dictates that time passes at different rates for different observers. This gives us two potential methods for leaping forward in time. The first is velocity. If you were to board a spaceship and travel at a significant fraction of the speed of light, your personal clock would tick more slowly than clocks back on Earth. Imagine a journey to a star 9.5 light-years away at 95% the speed of light. For observers on Earth, the trip would take 10 years. But for the crew on board, due to time dilation, only about 3.12 years would have passed. When they returned to Earth, they would have aged only a few years, while their friends and family would be decades older. They would have effectively traveled into Earth's future. The second method is gravity. Clocks run slower in stronger gravitational fields. If you could hover near the edge of a massive object, like a black hole, for a while and then return to Earth, you would find that far more time had passed on Earth than for you. Both methods are technologically far beyond our current capabilities, but they are firmly rooted in established physics. The most famous illustration of this is the twin paradox. Imagine two identical twins. One stays on Earth, while the other embarks on a round trip to a distant star at near light speed. When the traveling twin returns, she is significantly younger than her earthbound sibling. The paradox seems to arise when you ask, from the traveling twin's perspective, wasn't it the Earth that was moving away and coming back? Shouldn't the Earth twin be younger? The resolution lies in the fact that the situation is not symmetrical. The traveling twin is the one who has to accelerate, turn around, and decelerate. This acceleration breaks the symmetry and makes her experience of time dilation real and absolute upon their reunion. She really is younger. But what about traveling to the past? This is where physics enters the realm of pure speculation, and where we encounter the specter of paradox. The most famous theoretical gateway to the past is a wormhole, also known as an Einstein-Rosen bridge. A wormhole is a hypothetical shortcut through space-time, a tunnel connecting two distant points. While often imagined as a way to travel vast distances in space, a wormhole could also be turned into a time machine. If you could take one mouth of a wormhole and accelerate it to near light speed for a while, a time difference would develop between the two mouths. Stepping into the younger mouth could allow you to emerge from the older mouth at a point in its past. You would have traveled back in time. Another possibility involves creating what are known as closed time-like curves, or CTCs, paths in space-time that loop back on themselves, allowing an object to return to its own past. Some solutions to Einstein's equations, like those describing a rotating universe or a massive, infinitely long spinning cylinder, do contain CTCs, but these are generally considered physically unrealistic. The biggest hurdle for wormholes is a theoretical one. To keep a wormhole stable and open long enough for something to pass through, you would need a vast amount of exotic matter, a substance with negative mass or negative energy density. We have never observed such matter, and it may be forbidden by the laws of nature. Even if these physical hurdles could be overcome, we would still face the logical nightmares of paradox. The most famous is the grandfather paradox. What if you travel back in time and kill your grandfather before he meets your grandmother? If he dies, your parent is never born, and therefore you are never born. But if you were never born, you couldn't have gone back in time to kill him in the first place. This is a self-negating contradiction. A more subtle but equally troubling puzzle is the bootstrap paradox or causal loop. Imagine a time traveler is a great admirer of Shakespeare. He takes a complete collection of Shakespeare's plays, travels back to Elizabethan England, and gives the book to a young, struggling writer named William Shakespeare, who then simply copies the plays and passes them off as his own. The plays become famous, are preserved for centuries, and are eventually bought by the time traveler, who takes them back to Shakespeare. The question is, who wrote Hamlet? Not Shakespeare, he copied it. Not the time traveler, he got it from a book. The information in the plays seems to have no origin. It exists in a self-contained, uncaused loop. Physicists and philosophers have proposed two main ways to resolve these paradoxes, but each requires us to adopt a radical new view of reality. The first is the Novikov self-consistency principle. This principle states that any event that would cause a paradox has a probability of 0. In short, the laws of physics forbid paradoxes. You can't kill your grandfather because history is fixed and self-consistent. If you travel to the past, you are not changing it. You are becoming part of the past that always was. Any attempt to kill your grandfather would be thwarted by some mundane event. You'd slip on a banana peel, your gun would jam, you'd have a change of heart. This solution preserves a single, consistent timeline, but it does so at a great cost. It implies a deterministic block universe, where the future is as fixed as the past, and human free will is, at best, a powerful illusion. The second solution comes from the many worlds interpretation of quantum mechanics. This theory suggests that every quantum measurement with multiple possible outcomes causes the universe to split into multiple parallel universes, one for each outcome. In the context of time travel, any action you take that could alter the past simply causes the timeline to branch. You can go back and kill your grandfather, but you do so in a newly created parallel universe. The original timeline from which you departed remains completely unchanged. You would continue to exist, but you would now be in a different history, one in which you will never be born. This solution preserves free will and avoids paradoxes, but at the equally staggering cost of postulating an infinite number of unobservable parallel universes, constantly branching with every decision. The debate over time travel paradoxes, then, is not really about building a machine. It's a proxy war over the fundamental nature of causality, free will, and reality itself. Are we actors in a single, pre-written story, or are we authors creating new universes with every choice we make? The physics of time travel forces us to confront these ultimate questions. The time of our lives, a final reflection. We have journeyed to the very edges of physics, from the cosmic scale of Einstein's spacetime to the timeless realm of quantum gravity. We've explored a universe where time can stretch, shrink, and perhaps even loop back on itself. But now, let's bring this grand, abstract story back to the only place where time is truly experienced, inside our own minds. For all the talk of atomic clocks and universal laws, our personal experience of time, what psychologists call chronoception, is far from a perfect, objective measurement. Our internal, subjective sense of time is incredibly malleable, shaped by the intricate workings of our brains. We've all felt it. Time seems to fly when you're having fun, and drag on endlessly when you're bored. A moment of intense fear or awe can feel like it stretches into an eternity, a phenomenon known as tachypsychia. And there's the common perception that time seems to accelerate as we get older. A summer vacation felt like a lifetime as a child, but now years can seem to pass in a blur. Neuroscience is beginning to uncover the reasons for this psychological relativity. Turns out there is no single clock in the brain. Instead, time perception is handled by a highly distributed system involving many different regions, including the cerebral cortex, the cerebellum, and the hippocampus. Different systems seem to process time on different scales, from the milliseconds needed for motor control to the minutes and hours of our conscious experience. Our perception of time is influenced by our emotional state, the amount of attention we're paying, and even the number of new memories we are forming. One theory suggests that time feels faster as we age because we have fewer novel experiences. Our brain processes the familiar, routine information more efficiently, and this corresponds to a subjective feeling of time speeding up. Our brain doesn't just measure time. It actively constructs our experience of it. And so our journey comes full circle. We began with the simple ticking of a clock and end with the complex firing of our own neurons. We have traveled from Newton's steady, universal river of time to Einstein's warped, relative fabric of spacetime. We've seen how the unyielding arrow of time likely points from the improbable order of the Big Bang towards the ultimate chaos of heat death. We've peered into the quantum world, where time itself seems to dissolve into a timeless network of relationships, a frozen universe from which our sense of flow must somehow emerge. We've contemplated the frontiers of physics, where competing theories like string theory and loop quantum gravity offer fundamentally different answers to the question of whether time is real. And we've wrestled with the paradoxes of time travel, which force us to choose between a deterministic universe and an infinite multiverse. After all this, what is time? The honest answer is we still don't know. It remains the most profound and unsettling mystery in science. Is it the fundamental, independent dimension Newton and Einstein believed it to be, albeit in very different ways? Or is it a grand illusion, an emergent property of thermodynamics, information, and our own conscious perception? The quest to understand time is nothing less than the quest to understand the ultimate nature of reality. And as we continue to probe its depths, we are left with a sense of humility and wonder, standing on the shore of a vast, mysterious ocean, watching the moments of our own lives wash by, each one precious, fleeting, and utterly inexplicable.